This is my air compressor. Now, when I turn it on, it makes a really loud noise. But that's not the only thing that it does. On top of this, there's a couple gauges. Now, the one that we care about is the internal pressure gauge. Now, this compressor handles up to 100 psi. However, the manufacturer claims that it has a maximum volumetric flow rate of 0.5 cubic feet per minute. That value is at 90 psi. So, for all of my calculations, I will be using 90 psi. Currently, the room temperature in my room is 68 degrees Fahrenheit. This is very important for our calculations, as you'll see later. Currently, the atmospheric pressure in Fort Collins is 101.3 kPa. The actual compressor pressure we'll be using is 620.528 kPa. As I said, the room temperature is 68 degrees Fahrenheit, which just so happens to be 20 degrees Celsius, which makes our calculations a little bit easier. Now, the rated motor power, which is on the side of the compressor, says that the motor is a 1/3 horsepower motor, which roughly equates to 250 watts. I rounded there to make my math easier. The estimated isentropic efficiency, which we need for our calculations, I've estimated on the lower end of the spectrum, as compressors can run anywhere from 65% efficient to 95% efficient. I've assumed that this compressor is 65% efficient. Now, as I said earlier, the manufacturer claims that it produces 0.5 cubic feet per minute at 90 psi output pressure. We are going to find the isentropic work, the actual work, the mass flow rate, the actual exit temperature, the volumetric flow rate, and then we're going to compare that volumetric flow rate to the manufacturer claim. Now, coming over to our diagram here, I've drawn a depiction of the compressor. I have the atmospheric pressure at 20 degrees Celsius. I've converted that to Kelvin, and I have an inlet and an outlet. On the outlet side, the pressure is 620.528 kPa, or 90 psi, at an unknown temperature. The motor draws 250 watts from the outlet. We have a couple of assumptions that we have to make in order for all of our calculations to work out. Our first assumption is that we're working under a 1D flow, a steady state, an ideal gas condition, one inlet, one exit, and constant specific heats. The reason we can assume 1D flow is because if we take a cross-section of the inlet and outlet, they are on 1D. The reason we can assume steady state is because the compressor process is a steady state equation. We're assuming that air is an ideal gas in this case because that makes our calculations a lot easier, as well as air acts like an ideal gas under most conditions, including these. We can say that there's one inlet and one exit, as we know this is true on the compressor. There is only one inlet where it sucks air in, and only one exit where it lets the air escape into the compressor tank. Now, we're also assuming constant specific heats, CV and CP, because A, that makes your calculations a lot easier, and at this pressure and temperature, they are pretty much constant, so we can assume that they are fully constant. Our first step to finding the isentropic work is to find the isentropic temperature at point 2. Now, point 2 is that outlet. To find that, we're going to take our inlet temperature, which is that 293.15 Kelvin. We're going to multiply that by our pressure ratio, so the compressor pressure, which we've said is 90 psi, or 620.528 kPa, and the atmospheric pressure, which we have said is 101.3 kPa. Now, that is to the power of K minus 1 over K. Now, K is the specific heat ratio, in this case for air specifically. Now, this changes with temperature and pressure, but that change is very small, especially because we've assumed an ideal gas case. Now, to find this, it is our specific heat ratio, so CV over CP, which we've already assumed constant, so we can use the same value for every single point in our system. In this case, our CV for air at the atmospheric temperature and pressure that I've chosen is 1.005 kilojoules per kilogram Kelvin, and the CP for the same temperature and pressure I've said is 0.718 kilojoules per kilogram Kelvin. Now, these can be found through the thermodynamic tables. In order to save myself trouble, I found an online calculator that gives these values. Now, this leaves us with a K value of 1.401 approximately. So, to find T2S, our isentropic temperature, we plug all those values into our equation. So 293.15 K times 620.528 kPa over 101.3 kPa, all to the power of 1.401 minus 1 over 1.401. This gives us an isentropic temperature number 2 of 492.48 K. Now, in order to find our isentropic work, or W sub S, that is equal to the change in our enthalpy. Now, change in enthalpy is also equal to our CP, which in this case for air is 1.005 kilojoules per kilogram Kelvin, times temperature differential. So, in this case, our isentropic work is going to be 1.005 kilojoules per kilogram Kelvin times our temperature differential with that isentropic temperature 2 that we had just found. Now, this gives us an answer of negative 200.33 kilojoules per kilogram. Now, why is this negative, you might ask? Well, it's because we're putting work into the system. That seems slightly counterintuitive. Trust me, it'll all make sense later when we continue to work through this. But yes, it is negative because we're putting work into the system. All right, so we've ticked off our isentropic work. Time to find the actual work. Now, in order to find our actual work, we can use the isentropic efficiency for compressor equation, which is just that isentropic work divided by our actual work. So we can rearrange that to be work is equal to our isentropic work divided by our efficiency. Now, our isentropic work is what we just solved for, and that efficiency is going to be that 65% or 0.65 that we assumed earlier. This is still negative because, like I said, we're putting work into the system. This gives us a value of negative 308.2 kilojoules per kilogram. Now that we've found that, we can find our mass flow rate. So the work in, which is W dot, or our motor power of 1/3 horsepower, is going to equal our mass flow rate times that work actual that we just found. So we can rearrange that equation to be m dot equal to negative 0.25 kilowatts, or 250 watts, and negative 308.2 kilojoules per kilogram. Now, the reason these are both negative is because they're both work in. Both of those negatives cancel out in our division, and we get a mass flow rate of 0.0008112 kilograms per second. That is super small. This will make sense later. Now, we need to find our actual exit temperature. You might just assume, hey, isn't that just that T2S we found? No, that T2S we found is the isentropic exit temperature. We are looking for the actual exit temperature. They're different. But we can use that same equation that we used earlier to find it. So we take our actual work equal to our CP for air times our temperature 1 minus our temperature 2. Now, the temperature 2 is what we're solving for. This ends up being 308.2 kilojoules per kilogram divided by 1.005 kilojoules per kilogram Kelvin plus 293.15 Kelvin, which leaves us with a temperature 2 of 599.82 Kelvin. Now, this is pretty hot. It's about 65% the melting point of aluminum, or 933.15 Kelvin, which, ouch, if you touch that, that's really hot, but that's exactly why on the compressor, there is a large heat sink on top to reduce the concentration of that. We can put it all together to find that volumetric flow rate. Now, given PV equals RT and our m dot, which is that mass flow rate, is equal to our volumetric flow rate divided by V, we can rearrange our equations to be our volumetric flow rate at the exit, that's sub 2, is equal to our m dot times our ideal gas constant for air times our internal temperature, right, temperature 2, divided by P2, which is our internal pressure. Now, that ideal constant R for air is roughly 287 joules per kilogram Kelvin. We can plug all of those numbers into our equations as we have all the unknowns to solve for our volumetric flow rate at the exit as 0.00225 meters cubed per second. Now again, this seems really small, but the manufacturer claims 0.5 cubic feet per minute, which is a unit conversion that we need to do, as meters cubed per second is not cubic feet per minute. So we take our 0.000225 meters cubed per 1 second, we multiply by 60 seconds in 1 minute, and then we multiply further by 3.28 cubed feet cubed per 1 cubed meter cubed. This leaves us with a CFM of 0.476, or roughly 0.5, which is what the manufacturer claims. Good to know I'm not getting scammed by my air compressor.